So the first speaker is Mario Rodriguez. He will talk about an overview of Alice highlights.
Okay, thanks a lot. I hope that you can hear me. Yeah, yeah. Anyway, I have. Yeah. Okay, as usual, first of all, for the kind invitation, in principle, well, when Eduardo invited me, he asked me to talk a little bit about the cosmic program in Alice, but unfortunately, we're still under internal review of our latest results. So this is Paul intends to have a connection with the previous discussions. And also, of course, at the end, I will say a brief words about what we are doing. Also, I will try to uh, go more or less quickly. So, okay, in principle, this is just to put some context, especially for the students. No, in principle, we have, okay, this works. We can access to the nuclear matter that is created in heavy ions collisions, where we have, in principle, extremely large temperatures. So after this, at the very beginning of the collision, we have the confinement of quarks and gluons, and then we have the evolution of these systems. So in principle, we may have a description of the system in terms of the hydrodynamic evolution, and then at the end, we will have the... okay, gracias. And then at the end, we have an intermediate between the hydrodynamic evolution and the particles that we can reconstruct or track with the detectors. And in the middle, we have this hadron gas phase. So this comes from the beginning of the century, in the sense that Rick and CERN experiments, SPS, in principle, they show evidence of this state of matter that is called the quark-gluon plasma, where we have the quarks and the gluons in the confinement state. And of course, the main results from the Rick experiment is the observation of the strong electric flow, and of course, the observation of jet quenching. So, as you can see, these results are more or less kind of 22 years old. So, what is this for? Because we have some signatures of the QGP and heavy ions collisions. So, in principle, we may have a collective flow, radial and anisotropic. We may have long-range angular correlation, no? In principle, kind of a collective medium. And of course, we may have also suppression of high PT hadrons. We may evaluate the energy loss of some of the particles produced, and that can interact with the medium, and engagement of thermal photons. So this is summarized in these plots, very old plots, but we can see, I will show some results about this, new recent results regarding the elliptic flow that was observed at the time of Rick. And of course, also we can see that for different species of particles that interact with this medium, we have suppression, no, with respect to the transfer momentum. The transfer momentum, it's the component of the X and Y components of the momentum in the square root, in the sense that they are perpendicular to the X of the beam. So, and also, of course, we have some proofs that where we can try to estimate the temperature of the system using the direct photons, also sometimes called the thermal photons, in the sense that measuring the energy of these photons, we can have more or less an idea of the temperature of the system created. And also, well, this is kind of tricky because we have to distinguish between this kind of photons and those coming from the pion decay. So more recently, now we have the LHC results, the observation of long-range near angular correlation in lead-lead and asymmetric systems like proton-lead collisions. Also, we have results now where the matter that is created in heavy ions collision that behaves like a fluid and with almost zero friction. And this is related, no, with the previous discussion uh, with the enhancement production of multi-strange hadrons. No, in high multiplicity proton-proton collision, this is new, and also from the uh, latest ATLAS results in 2021, angular correlation also in photonuclear ultraperipheral net-lead collisions. So this is just an example now where we have here one of the results of the plots that are shown commonly for the people from the STAR experiment, where we have the two jets. One is a quench jet, interacts with the medium, and we have this asymmetric distribution in the space and with respect to the phi component. And also this is a very nice D-jet event reconstructed by CMS collaboration like 14 years ago, where we can see the asymmetry, in the reconstruction of the transfer momentum in this DGET. And also these very nice results coming also from CMS collaboration, where we have a near-side peak here, but in proton-proton collision that it was unexpected at the time. And in principle, it's leads to open new area, at least in the within the ALICE collaboration, in order to try to explore as much as possible all the properties of this kind of system produced in proton-proton collision. So this is just to give an overview of the current situation of ALICE collaboration. Up to now, we have like 2006 members coming from 40 countries around the world, 169 institutes. And this is just a photograph of from part of the detector. So ALICE is optimized, of course, for the study of the matter produced in the lethal collisions. The aim is to study the physics of this strongly interacting matter, looking at the different groups that we can have for the formation of the quark plasma. And of course, this detector was designed for the LHC energy. So this is just more an schematic of the detector, where we have, you can see with respect to the ATLAS or CMS detector, we have 18 subsystems. So it's not so trivial to put together in order to take data from all the points of view. And I will show only the characteristics, general characteristics of the detectors that are commonly used in the studies, the results that I will show today. First of all, the minimum bias and centrality trigger detector, the B0, that it's located plus or minus 3 nanoseconds, 11 nanoseconds in time, in opposite location around the interaction point. This has a coverage in one side from 2.8 to 5.1 and minus 3.7 to 1.7 in pseudo rapidity units. No, it's a very nice detector because we have a good performance of the B0 detector, and also it has a possibility to have to provide a centrality trigger for different kind of studies, and also as a reference multiplicity estimator in different studies. No, of course, this is one of the big advantage of this detector. We have gas detector that is called the TPC, time projection chamber. We have the possibility to tracking charged particle, and also to make all this possible with the identification via the DADX in eta an absolute value less than 0.9, very central events. We have the internal trigger system that it's formed from silicon pixel detectors in 2 layers, one internal, one external, SPD and SDD. And in principle, we can have tracking as well, but also the reconstruction. That this is a very good advantage with the reconstruction of primary and secondary vertex in the same region as the TPC. Also, we have in a very specific region of the detector, the high mu multiplicity PID, high momentum, sorry, PID detector, HMPID, for the reconstruction of the identification of high momentum charged particle in a very specific azimuth angle and also in a very specific pseudo rapidity range. No? And of course, we have another technique for the identification of particles using the time of flight, that it's a gas detector. And I reach to the timeline outline of this experiment. No, we have here the different version of the detector. We started taking data in 2009, 2013, proton-proton, proton-lead, lead-lead collisions in round one. Then we have the round two between 2015, 2018, in this different system, proton-proton, asymmetric system, proton-lead, lead-lead, and xenon-xenon. And after that, we have upgrade program that we call Alice 2. We are here in July of 2024. The round three, of course, in the morning sessions, also it was a discussion about the proton oxygen that in principle is expected for the next year. No. And for the round four between 2029 and 2032, we will have Alice 2.1, where we will have an inclusion of a very specific forward calorimeter that is called focal. And for this system, proton-proton, asymmetric, and lead-lead. No, in principle, we have a mixture here for high luminosity for ions. And of course, we're looking to the future, starting from more or less 10 years from now, in round five, high luminosity LHC, that in this case, the detector will be Alice 3. You can see that we will modify most of the geometry on the detectors that we are developing right now. So this is just a timeline of the Alice physics paper. We have submitted almost 500 papers. And at the end, this is just a summary of the data that we have acquired in 2022, 2023, 2024, and also how it's compared with the data taking from round one, from round two. You can see that we almost double the integrated luminosity with respect that we have in the previous round. Now this is 2023 lead 5.36 TeV. So this is a kind of compilation of all the results that Alice has obtained during the last years. This is the Alice experiment, a journal through QCD that it is accepted for publication. It will appear soon. And just I list here, I'm not sure if they are the main results from Alice, but just to highlight the titles, you can see that the main contribution comes from the studies on electric flow, correlation, angular correlation, and of course, a study of specific production of particles, pions, kaons, protons in different systems and how it depends on the centrality. And of course, the enhancing production of multi-stretch hadrons, specific particles studies in lead, and also multiplicity dependence in proton-proton collision, no, for multi-stretch hadrons. And of course, I have doubts in put 2 or 3 slides, but it was presented this in the last symposium. Work done for the collaboration where it was a measurement of the anti-helium nuclei. And in principle, this is related, no? Transparency of the galaxy that was presented before. And also we have here a work that is more dedicated in the study of cosmic ray using the tracking capabilities of the Alice TPC. Also, in principle, we can try to summarize this looking at this table where we see the reconstruction capabilities of a detector, different particle species over this PT range, starting from low PT up to 40, 50 GeV overs, no? So at the end, we can summarize this with the different reconstruction capabilities of detector, different techniques, using the solid state detector, gas detector, etc. So you can see that we have very good capabilities for distinguish the particle species for different ranges of momentum. So we may have this uh, description of the angular of each one of the particles that are created in heavy ions collision. So we may have some attention to this parameter that is called usually the flow parameter. So in principle, we are able, using the specific dedicated detectors, to have reconstruction of this quantity. In principle, we may have a result like this. One of the first results given by Alice like 14 years ago, where we see that the measurements from this experiment from Ali show that we may have an elliptic flow of the charged particle, that increases more or less in 30% with respect that we have in the case of a star. So not going into details, this may indicate that we have matter that is created with it behaves, sorry, like a fluid with almost zero friction. And also we have some studies now, the long-range angular correlation that are comparable with the previous measurements given by Alice, CMS. And of course, we have recently the Strange Quantum Conference last month. So I took 2 or 3 specific studies from the colleagues that presented this. And this is related also with the angular correlations, but for a strange hadron, where we can see here different configuration. Let's say we have cascades, chaos, and we have what we have here a specific description where we have correlation between particles with opposite sign, between particles with same sign, etc. And we can see, or we can try to have a look to the angular correlations using these definitions, and also to have a comparison with the different models. No, for this case, it was a comparison Pythia, Herwin, and Ipos LHC. And with this comparison, we can see things like this. Now, Pythia, Herwin predict a narrow and taller nearby side. This is blue. This is kind of pink. These two. And also, we have another configuration from Pythia with Robson functions, and maybe provide a better description than the Pythia twin monage. No, and of course, we have also the prediction given by Ipos LHC with a broader peak, this one. So this is regarding the flow angular studies with the strange hadrons, and also here, as I said at the beginning, it is very interesting, and many people in the collaboration is working on the characterization of particles created in the small system, proton-proton collision. So we have here a plot where we see the dependence of the mean PT value with respect to the number of charged particles in a very specific pseudo-rapidity range between minus 0.5 to 0.5. So we can see that the multiplicity of this mean PT increases in proton-proton system. Of course, we can see here kind of different behavior with respect to the for higher hadrons masses, no? So in principle, this make us an indication, a possible collective evolution in a small system. No? This is kind of similar to the previous one that I presented to Raya. No? And of course, the strangeness itself represents a very good proof for the studies of the quark-gluon plasma. We have here this of the very well-known results from Alice, where we can see the ratio to yields ratios on the specific particles respect to the pions produced in the collision. No, so in principle, we have an enhancement of the production of these strangens, and also we don't observe a dependency with respect to the system. No, proton-proton, proton-lead, lead-lead, and early comparison with different models. No, and we have also more or less analogous study for Alice proton-proton and 30 TeV, where we compare this, and also we see again that the yield of these strange hadrons increase with the charged particle. And the interesting thing is that the trend is the same at 7 and 13 T. So this is quite interesting in this sense. And also, we may have a look to the mean value of the transfer momentum with respect to the multiplicity of charged particles in this specific range of eta. And also, we can see that we have a strong connection between the PT with respect to the different system. So also, again, we can see ratio now of the yields for these particles with the structures with respect to the number of pions produced in the proton-proton collision. And again, we can see that for different energies, for 7, 13, 2.76, 5.02, in the case of lead-lead, proton-lead, and small system, more or less the same. So this is something that was presented recently in the Strange But Matter. So at the end, this may have a connection, as it was proposed by Luis Ancondoki in his paper, and where they made a comparison using EPOS, QCHZ civil for different systems. In principle, we may have a connection here, no? And also I made a quick modification to the original slides because taking into account one of the talks of the morning session regarding the photo production. So also in Alice, taking advantage of the trigger capabilities for the minimum bias trigger detector, we can distinguish between central, semicentral, peripheral, and ultra-peripheral collision, where we may have electromagnetic interaction between the electromagnetic components from both pins and also between the gammas and the nucleons from the other beam. So in this sense, there are many kinds of studies that we can perform, also studies related with the cold nuclear matter effects. But in this sense, well, this is more schematic view of ultra-peripheral collisions. We are able to have identification between coherent and incoherent processes. This is the differential cross-section with respect to Y that we measure at the very beginning, where we have an energy of 2.76 TeVs. At that time, we performed this study in two parts. The first one was for the forward region. The another part was with the central region, what we consider also the electron positron decay of the psi. For the forward region, we only consider the psi going to muons, and we have here the reflector results. So in principle, we found at the time that the best agreement is found with models which include a nuclear shadowing consistent with these two parameterization. This is, of course, regarding the, I think here, vector mesons particles, but also we have recent results. Have a look to the archives. In principle, they will appear in PLB regarding the photo production of 4 pions. Now we have here the invariant mass distribution for the data that we collected in lead-lead collisions, ultra-peripheral, of course. And you can see that we performed a study assuming the production of 2 resonances, the rho 4050, rho 7000, and a kind of interference. So we have these 3 cases, and we estimated the cross-section for the different cases. So in principle, the invariant mass distribution of these 4 pion events photo produced in the heavy ions collision are best described with this fit, assuming these 2 resonance and 1 interference with them. So you can see that we have very good capabilities for the strangeness reconstruction. And also, as I said at the beginning, we have the possibility of tracking cosmic muons. So we may have the reconstruction of the muon multiplicity distribution compared with the 2 models, with the models, assuming heavy and lightest component. And also, of course, we can estimate at least the rate of events with a large number of muons underground and compare it with the data. These are those 2 visualization of this kind of bundles that we are able to reconstruct. And again, the theoretical community started to work on these events recorded by Alice, assuming some kind of strangelets produced. So as I said at the beginning, we have the run-2 data sample. We doubled the statistic. The paper is under collaboration review. And now we have a comparison with EPOS LHC civil QGZ 204 with the new Alice data, but unfortunately, I cannot show the final results. That's why they are here. Also, this one where we compare we have to send to the journal the next year. So next semester. No, so just going quickly, this is regarding to the upgrade going to Ali stream. In principle, we want to improve the resolution at very low PT. And this is very interesting. The point of view, we are proposing a muon ID detector. And you can see that we will increase the acceptances with respect to the current ALICE, to this one for ALICE 3, and also this is ALICE 3 versus ALICE 2 for the estimation of PT for lambda particles. No? And this is just a list of all the studies that we are thinking of, the performance. Also, we have performed some studies at the T10 at CERN facilities. And what happened? Oh, so I just left this as my final point. Thank you.
Thank you very much. Are there any questions?
Here I go.
Could you go to slide 33 about the strangeness production compared to models? Yeah.
This one, yeah.
So there is this model DIPSY, I think, which is also Lund, right?
Yeah,
which describes it reasonably well, the strangeness. Could you elaborate a bit on that? What is different there compared to PCA and EPOS?
Well, I don't have the details, no, the detail between them, but in principle, there's some work in the collaboration where they are trying to use recent version from EPOS, for example. Unfortunately, I cannot show, but we have this kind of studies.
Okay.
More questions?
Thanks. Thanks a lot. Yeah. What is the main purpose of the upgrade of Alice once you go to high luminosity LHC?
Yeah.
Because right now, my understanding is you basically don't run into situation with tracks or something because the detector is forming well. Is it that you want to increase the rate, the data rate, or is it something else?
Okay, I have this. Yeah, this is something that will go into details. No, we in principle intend to have better precision in the measurements of the dilepton spectrum. This is the main objective. That is why we're trying to improve trigger capability for muons. Yeah. Yeah, yeah.
You know, from the people who run models, they would love to have a lower PT cutoff in your data because you typically have like a minimum PT for which you then give the charged particles and other things. If you could fix that too, that would be really nice, but it's a completely different thing.
Yeah.
It's yeah, good. But yeah. So but it's you are going to change the detector during one of the breaks, or is it actually?
Well, we
Because
have.
it wasn't obvious from your timeline that
Yeah.
HC will be turned on off at this time. It looked almost like it was in the data taking period of high luminosity. Let's see.
Yeah. This one up. Yeah, between the in the break, in the forthcoming break, we will put forward calorimeter.
Yeah.
This is the main upgrade that is Alice 2.1.
Thanks.
Any other questions? In Zoom, maybe? No. Okay, so let's
Thank
thank
you.
Mario again. And now it's Dennis Soldin, astroparticle physics with the Forward Physics Facility.